Okay, welcome again. We're going to try to finish with nonlinear solvers today. First, thank you for those who took the survey on class participation. I'm assuming those who did not take it, you want to be on the on-call list. You have the option to opt out, opt back in anytime you want. But I hope those who chose to be on the no-call list to reconsider and let me know, send me an email personally, and we can have a chat about how we can make kind of things a little bit better for you if you want to try at participating. I think it will be a useful thing to practice with. I'd like to have your names up front, if you don't mind. We are going to start today with the life hack, okay? So in a minute, when there's some quiet, Lev is going to deliver our life hack today for the day. Do you want to come up here? You want to? All right. Okay, so Lev is going to give us the life hack today. You're welcome to stand up and or come up here or stand up and tell us about the life hack. Guys, if you would listen, please, to Lev. All right? Great life hack today, I hear.
So the life hack that I have, life hack I guess, is basically if you ever get battery acid spill, which happens when you're working on cars and just multiple things, the best way to clean it up is first to neutralize it with baking soda, and then you're able to clean it up with a dry paper towel after it has stopped reacting, aka it stopped fizzing.
Oh, perfect. Thank you. Hey, thanks. Good life hack.
Also, if your battery gets really old in your car, you can put baking soda in the little terminal.
Oh, to clean it up? Okay, well, thank you. Another life hack. All right. Who wants to do a life hack on Tuesday, next Tuesday? All right, we got, remind me of your name. Nate. Okay. Yeah. All right, so next time it's going to be Nate. Okay. So I want to show you a little calendar of where we are. Okay, we are on February 9th. Okay. So I had you are here first, but technically this is time, so you are now. This is now, right? And homework 5 is going to be assigned today on nonlinear solvers. Homework 4 is due today on linear solvers, okay? Next Tuesday, we're going to have a standard lecture. Then next Thursday, we're going to do exam 1 prep and discussion, okay? Because exam 1 is going to be here on the 23rd. All right, so I want to give you at least a weekend and a few days to come and ask questions after you study so that you're ready for the exam, okay? Homework 5 will be due on next Thursday, but there will be no homework assigned, okay? So for that week, you're only focused on studying for the exam. On the 16th, we'll talk about the details of the exam, what to expect, okay? If you're starting to study from now, do not study programming things. You're not going to get syntax questions or NumPy questions. Do not spend any time on programming, okay? The only type of question that is even related to programming might be, for example, what inputs would you provide to a Newton method, right? Which is still not really a programming question. It's more of a hypothetical question. Lev? Yes, so we're working on that, and there's going to be a study guide and practice exams that will be provided to you. Most likely the exam is going to be an online type exam with many low stakes questions that are quiz style questions. So what that means, you study the lectures and pay attention in class. Rachel? It will be open notes. Okay, so I'm going to discuss all of that. It will be open cheat sheet, not the lecture notes, okay? But we'll discuss that on Thursday. Yes, Brandon?
Is this the only exam we have before spring break?
I believe there's going to be, I don't remember the dates. I don't remember the dates. Probably Yes, probably there might be another one. I'll check on that. So on Thursday we will talk about all of those details. For now, if you wanna know more about the exam, go to the syllabus. The entire plan is laid out over there. Okay, the plan is laid out over there. What to expect for the exam, etc. The feedback surveys that I asked you to do, those are going to be the foundation for the study guide. Okay, there's over 90 questions on on errors and linear solvers, and other 80 questions or so. So those are going to be fantastic study guides. Okay, but again, the slides are critical, and things that I discuss in class with you, those are critical. So paying attention is going to be important. Okay. All right. So when in doubt, that's going to be a question. All right? But that's not on the slides, right? So, okay. And then on the week of the exam, I'll be here. If you see me and my door is open, if I'm around, just come and knock. If I'm not on a call or something, I'll talk to you, Rachel. Okay, so open door on my laptop at home. So you can email me, and I'll be happy to chat with you and talk to you. Okay, we can even do Zoom meetings if you want. Thank you for that. Okay, on Tuesday there's going to be a help session and a lecture, and clearly I will be there as well. If you want to stop by and talk to me, talk to the TAs. On Wednesday there is office hours, but there's also I'm there through the entire day. Lev. Nope, has nothing to do. Nope. These two lectures are not going to be on the exam. Okay? So we stop the exam, and we'll talk on Thursday. Okay? The exam is going to be up to nonlinear solvers. That's it. All right? And then exam 1. Okay? Okay. For the nonlinear solvers, we're going to continue. Last time we left off trying to do this nightmarish equation, solve it using our Newton method. We had to put in the residual, but then we had to put in this nasty derivative. Anecdotally, half the class didn't get it right because they had typos and mistakes. Even I had typos in the derivative. And that's good because that proves my point. Because it proves that putting in this derivative is painful and it's prone to errors. Okay? So, now I ask you this question, using what you know so far, numerical methods, what we've seen from day 1. Do you have any suggestion on what we could use as an alternative to using the derivative, doing the derivative by hand and programming it? Group activity, okay? So remember, Newton's method has a derivative in the denominator, right? I'm sure they are. What is H? Okay. All right. Any takers? Tomas, Brandon, Rachel, group over there. Pardon me? Okay. Oh, that's right. You're the Jeff Silcox group. What are you thinking? Could we do the derivative without actually calculating it by hand, deriving it by hand analytically and programming it? Okay. But we've seen it before. Okay? And let's see, another group. So Connor alluded to that last time. Maybe we'll have Connor volunteer that information. I'm volunteering you to volunteer that information.
We can just take the approximation of the derivative of f(x) plus h minus f(x) over h
Uh-huh.
that we can use that, the value we get out of that as our
Exactly. And what would you do for h?
really, really small number.
Just as use a small number. Yes. Okay. So what Connor suggested is, instead of computing this annoying derivative, when I say computing, instead of having to derive it analytically, to me, I had to put it in Mathematica, do the differentiation, and then type it up, and then we had to program it, and we made a mistake. Instead of doing all of that, we can just use f and use an approximation to the derivative. Remember that forward Euler difference, f of x plus h minus f of x over h, right? We can just implement that, okay, with an arbitrary value for h to approximate that derivative, okay? So there are actually several of those approximations. We will learn in a few weeks how to derive other approximations, but that's the one that you're familiar with. The derivative of r with respect to x is rx plus delta minus r of x over delta, and delta can be chosen arbitrarily. There's a guideline of how to choose this delta. If you remember also one of your homework assignments, or one of the things we did in class actually, we saw how if we kept decreasing delta, there was a point where round off took over truncation error. So you can't use delta very, very infinitesimally small, right? But any value for delta is going to be sufficient. Any sufficiently small value for delta is going to be sufficient to compute this derivative. Now, these are different approximations for r prime. You will learn in a few weeks how to derive those. But what you should note here is this order for the truncation error, okay, which is related to the error. Okay, the error here, we call this a first order error. Again, you will learn about that. And we call this here a second order error. This is more accurate, this formula here, but it has two function evaluations. This one does have two function evaluations, but remember r of x, we're already computing it in the numerator. Okay? So in terms of cost, this is a little more costly. If you're solving the system 10 iterations, that's fine. But if you're doing the equation, you're solving the same equation over and over again for millions of iterations, any function evaluation saving is going to be useful, okay? So the point here is that you can use any of those derivatives to compute, to approximate any of those approximations to approximate the first derivative, okay? These first order methods are cheaper, they're less accurate. This second order method is more accurate, but requires more function evaluations, okay? So when you look at Newton's method, again, what's a function evaluation is when you evaluate r of x or f of x, okay? Because in the code, in the software, in the program, that has to go to a different part of the code, run, evaluate the function, store it in memory, pass it back to the main routine. So that happens in the numerator, f of xk or r of xk. And then in the denominator, you already have r of xk evaluated over here. So you don't evaluate it again. You just evaluate this one or this one. But for this guy, you have to do two more evaluations, okay? So it's a little bit more costly. Now, some hints on choosing delta. I always like to choose delta to scale with the initial guess, okay? So for example, I take the initial guess, multiply it by some small number. Okay, I base it on the initial guess, take that initial guess, multiply 10 to the minus 5 or 10 to the minus 4, and add a very small number in case your x0 is actually 0. Okay? And when you do that, then notice your Newton method no longer depends on a derivative. So the inputs for the standard Newton's method were f or r prime, and a tolerance and x0, right? In this case, you don't need f prime anymore because you can evaluate f prime internally within the subroutine itself, okay? So let's go ahead and do that together. I'll guide you through the programming. Okay, so open up your notebook that we opened up, that we were working with last time. We already have our residual function defined there for that pipe spilling problem. Remember, we had the water spill, and the maintenance worker was going to go and walk inside, etc. So let's open up that one. Let's see. All right, I'm trying to, okay, there it is, this notebook over here. Okay. Right, so that's the notebook we were working with last time. Okay, we had those, remember, we had those values, and we had to define this residual derivative. Okay, we had the standard fsolve for pipe residual. We had the standard Newton method that took the derivative. This might still not be working with you, for you. And you know what? Let's do the other way. Let's do it without a df. Okay, so let's do define. Actually, I'm just going to copy everything here. I'm going to do def Newton 2. In this case, I don't need a derivative anymore, because we're going to evaluate the derivative internally. We're going to approximate it internally. Okay. Everything else here is the same. Okay, except we need to evaluate a df. Okay, so here's what we're going to do. I'm going to say df is equal f of x plus delta, let's call it delta, minus, actually f of x0, sorry. Oops. F of x0 plus delta minus f of x0 over delta. And the way I type these Greek letters is I put a backslash, I spell the word delta, and then I press tab. Okay? If it's not working, call it D or H. Okay? Just give it another symbol. So we agree that this gives us now the value for the derivative, or for the residual function, the derivative of the residual function. And then our Newton method is simply going to be substituting this denominator. Instead of df of x0, now it's just df, right? Because it's just a variable here. We still need to define delta. So delta is equal, I'm going to do 1e to the minus 5 times x0 plus 1e to the minus 12. Okay. Now, if you're ready, go ahead and call this Newton method Newton 2. And then what we're going to do, we're going to pass the pipe residual, the residual function, our initial guess, which was 1.0, and our tolerance, 1e to the minus 8. And look at that. It gave us the same answer as the other one, right? Miles?
Where do we get 1e to the minus 12 from?
It's just an arbitrary value. You could put 1e to the minus 10. It's just a, in case x0 is 0, I don't want my delta to be 0. So I'm going to put a small value so that it doesn't trash the denominator, okay? So you can put anything here. You put 10 to the minus 8. 10 to the minus 8. It really doesn't matter. Try it with any value. Okay, so I can try it with 0.001, okay? Just works. Yeah, to make sure delta is not 0, if I'm scaling it with x0, okay, I make sure that, so 1e to the minus 4 or minus 5 times x0 plus 1e to the minus 8, okay? There are other ways. So first, do we get this answer? Are we getting this? Yeah? Okay. No? Yeah? Okay, maybe your residual function is incorrect then. Did you get the correct answer from fsolve? 1.505. Did you get 1.505 from fsolve? Yeah. Okay. There are other ways to approximate this derivative if you're confused about delta. We can take, for example, the two previous iterates and do, rise over run with the two previous iterations without having to worry about delta, but that becomes a little of a specific point, okay? But the point here is that we don't have to put in the analytical derivative. Practically, putting the analytical derivative is always better, okay? Because that gives you the best accuracy possible. But in practice, we rarely do that because they are very painful to obtain and to implement. They're always prone to errors. Ian?
How come the second number in that is to the negative 12, when in the first one it was to the negative 14?
Where? Oh, yeah, this is the error at the end. Okay, this is the error committed by obtaining this root. Now, this error is a little bit, anything with 10 to the minus 12, 10 to the minus 14 is significant. But let's, for the sake of the argument, suppose that this error, suppose that we're trying to compare the error committed by this method to the one with the exact analytical derivative. Which one do you think is going to give us a slightly higher error? The one with the approximate derivative, right? Because it's not an exact derivative, right? So that's what's happening here, okay? We're committing a little bit more of an error with approximating the derivative, but it's really insignificant, okay? Okay, fsolve internally is doing that, okay? Because you don't provide fsolve with a derivative. You have the option to provide it with a derivative. If you go to fsolve and enter the parentheses and shift tab, you see f prime over here. You have the option to give it an analytical derivative, okay? But you don't have to, okay? All right. Okay, so now, remember, Newton's method was, you start with an initial guess, you draw a vertical line, you hit the function, you draw a slope, that's your next guess. You draw a vertical line, you hit the function, you draw a slope, that's your next guess, etc. Now consider this function, x cubed plus 5x squared plus 2 is just a standard cubic polynomial. It looks like this. We know there's a root over here, okay? Now, I want you to draw this curve on a paper or something, and start with an initial guess at x minus 2, okay? And tell me what happens if you try to apply the Newton method. So at x minus 2, draw a vertical line. You hit the function, then draw a slope intersected with the x-axis. You're going to get here. Then keep repeating that same process, and let's see what happens. Just do it a couple of times. So the point of this exercise is to show that choosing a bad initial guess, you're not going to converge anywhere. So draw a vertical line. You hit the function. Draw the slope. You hit the x-axis. You'll be here. Yeah. Let me. Hold on. Let me bring this a little bit down so I can point my finger. Okay. Okay, now this is easier. Okay, so draw a vertical line from x equal minus 2. Then draw the slope, okay, the tangent line. You intersect the x-axis here. That's your next guess. Draw a vertical line, then draw the slope. You're going to get here. Draw a vertical line, draw the slope. You're going to get here. Draw a vertical line, draw the slope. You're going to get here. And then you're going to keep swinging back and forth and back and forth. Do you see that? Yeah. Okay. If you don't see it, let me show it to you. In a Python demo, if I can find it. One moment. Okay, Nonlinear Solvers, Newton demo. So what I have here is a long, detailed notebook. You don't have to worry about it, but if I run it, let me see. Okay, so I should have a point over here, and where is that? Do you see a small window with a button on it? Do you see a small window somewhere with a little button on it? One moment. Sorry. It's always messes that up. One moment, please. Okay. Okay, so now I can get back here. So what I have here is an interactive Python notebook where I'm going to show the function. Okay, this is the initial function. Okay, and I have a little button over here. Okay. So we agree that this is the function we're looking at, right? That's our initial guess at -2, this blue point. And then our next guess is going to be here. Agreed? Draw the slope, intersect here. Okay. So now the next one is going to be a slope, or the tangent line, at that red point. So let's do it. Iterate. Okay. So now that's the next guess. Then the next guess, 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 next guess. It's going to keep oscillating and oscillating back and forth. It will never converge.
That's bad.
It's bad. Because we chose the initial guess on purpose in this case. It was close. It was in a local minimum. So when you don't converge, what do? If you can't plot the function, just choose another guess. Okay? Most cases, you can draw the function. Take a look at it. Okay? Stay away from local minima. Over here, this -2 is within this local minimum. I would move it kind of over here to -4, and then it's going to converge directly. Go to it will be a nan. Yep, it will be infinite. It will be not a number. It will diverge. So when you see Python spitting out this pink message, like couldn't do any improvement, it's not converging, it means there's something going on, like that. Okay? Might be stuck in a local minimum or something like that. Mm-hmm. Yeah?
In a situation where there's a local minimum that is within the tolerance of how far, like for example, if your tolerance is say 10, in this example, could it just give you a wrong route?
Yeah, it might give you a wrong route. That's a good point. So what Miles is saying, well, what if my tolerance was this much? Okay, now, in that case, that's a bad choice for a tolerance because this function varies quickly. So in your situation, if the tolerance is 10, I would imagine the function is not varying that fast within that interval, right? So it would probably be just a straight line within that interval, okay? So this function is the scale on this function is probably on the order of 1, okay? Because it's changing very quickly as x is changing, okay? So yes, you're right, but then I wouldn't choose that kind of tolerance for a function like this, okay? But yeah, you're right. It might say, oh yeah, I found a root, okay? Mm-hmm.
I noticed with the Rapson method with the approximation of the derivative, at least for mine, maybe it's that wrong. But if we make h too big or too small, the h that we're adding to it, it doesn't converge.
Okay.
Is that just because it's like having a hard time getting?
It's a bad approximation for the derivative, yeah. It's getting the wrong slope, really, yeah. And we can look at that after the class, kind of more specifics, yeah. Yeah, see what's happening. Okay. All right, so I want to get to systems of equations, and then we will call it a day. Okay. All right, systems of nonlinear equations. I'm going to come back to the heat transfer problem. It's not that I'm obsessed with heat transfer, but it's like these are some of the best examples that I can give you, you know, at this stage that you can relate to and get excited about, that these are some realistic problems that we actually deal with. So we're going to consider the same rod. So far we had that rod with a heated source, like a match or a lighter, light heating it. That was S of x. Then in your homework 4, you did the rod subject to cooling from the air or heating from the air, right? So that was called convection. Okay, so far, the first heat transfer problem we covered, you learned that's called conduction heat transfer. It's when heat transfer occurs through molecular interaction, solid to solid, for example, or gas to gas, okay? But then the problem you solved in your homework assignment is called an advection type problem because there's an interaction between two different phases of matter. There's the air heating or cooling a rod. Now, within the rod, there's still conduction going on, okay? But the air is also passing or taking out heat out of the rod. The third mode of heat transfer is radiation, okay? And this is going to be a radiation problem. We're going to take that same rod. We're going to fix the temperatures, but we're going to put it in an oven, okay, with heating elements, not a convection oven, just like heater elements like these ones at the bottom, okay? And they're going to heat up the rod. We're fixing it at both ends. Imagine you have like I don't know, you're cooking an eggplant or something, and it's kind of spinning slowly, and it's kind of warming up, okay? But then the equation in this case on the left-hand side looks the same because this is just heat diffusion. But the right-hand side, or the source term that is causing the change in the heat in the rod or the eggplant is through radiation, and it's given by that formula, alpha t to the fourth power, okay, minus t infinity to the power 4. Now, when you think about this right-hand side is a very nonlinear source term, okay? It's a nonlinear source term because the variable in question, which is temperature, shows up nonlinearly. In the first source term problem we dealt with, we had an exponential whatever, but it was a function of x. We knew what the value was. In this case, we really don't know what the value. It's coupled to the equation. You will learn at the end of this course how to discretize this equation, but I'll give you the formula here, okay? Just like we did with the other heat transfer problems, we can convert the second derivative into a discrete approximation, and the right-hand side is evaluated at any point I in the rod. So you're familiar now with this procedure. Okay. Now, however, this equation for the unknowns ti plus 1, ti minus 1, is it linear or nonlinear? Nonlinear, very highly nonlinear, okay? Because you have this ti to the power 4. So at the end of the slides, we're going to create the system of nonlinear equations, but actually, we're going to create them right now. So at the left-hand side, you got t0 is given to you, t left. And then at the first point, you got t2 minus 2t1 minus alpha delta x squared t1 to the fourth, etc. And then on the right-hand side, it's a constant, right? Alpha delta x squared t infinity. Those are constant values. Then you continue all the way to the last point, okay? Each one of those equations is a nonlinear equation, but you cannot solve it alone because it depends on two other temperatures. So this second equation here, t2 minus 2t1, etc., that's at point t1. But it depends on t0, which you know, but it also depends on t2. You don't know t2, but the equation for t2 is given by this one. It's also nonlinear. For t2, you need t3, and it's given by this one, which is also nonlinear, and so on. So that's a system of nonlinear equations. Very, very important. For a system like this, you cannot plot it. You have no clue where the roots are. No clue. So we're going to learn now how to solve a system of nonlinear equations. We'll start with a little example. I have two functions over here. Half x cubed plus y equal 4x, and y equals sine x e to the minus x. And they're shown here. One of them is in black, one of them is in red. I don't know which one is which, but they look funny and interesting, okay? Now the question is, what does it mean to solve a system of equations, of nonlinear equations? And I can only do this for an example that's simple like that, where you have only two unknowns, x and y. Once you go to more equations, you can't visualize it clearly and cleanly. So give it a moment. With the single equation, we said solving that equation means finding the value of the unknown, or the variable of interest, or x, where that curve intersects the x-axis. Now, when you have two or more curves, two or more equations, what does it mean to solve those two equations concurrently? Right? The first equation depends on x and y, and they both depend on each other, right? You shouldn't know the answer, but I want you to take a guess at it. Okay? Okay, so okay, 4 of what? Intersections, yeah. So you're thinking that solving these equations means when they are like touching each other, when they're like equal to each other, yes. So solving a system of nonlinear equations, whether 2 equations or a million equations, is finding those points where all of those hypercurves touch each other. Over here, it's simple to visualize because it's a simple 2D situation. But in higher dimensions, that's what's happening. All of those curves intersect each other. And you can imagine how annoying and complicated that problem is, okay? And it is. So visually, graphically, it means finding the points of intersection, okay? Now, we're going to standardize the procedure of solving a nonlinear system of equations by writing it in residual form. So for a single equation, it was obvious. You move everything to kind of one side, right? And you set equal to 0. But for a system of equations, what do? You do exactly the same thing. You take the first equation, and you move everything either to the left-hand side or to the right-hand side. You take the second equation, move everything to the left or to the right, okay? And that's implicitly, now we're solving this system when they're both equal to 0. So now this amounts to finding the values of the variables of interest, in this case x and y, such that both of those residual functions are equal to 0, which means they're also equal to each other. Okay? They're also touching each other. Okay? So that's the standardization. Okay. So here's where we're going to take a detour. We're going to say Newton's method can be extended to a system of nonlinear equations. And this is usually where I lose the class because it gets exponentially very complicated. So this year, I decided that it's not going to be useful to study Newton's method in higher dimensions. If you're interested in seeing it, it's at the bottom of the slides. Detailed derivation, and I have videos about it on YouTube. But it's not necessarily very helpful for you to know how the details work. It looks exactly the same as the standard Newton method, but you're going to have matrices and Jacobians in it. So it's a little bit kind of beyond what we really need to know to be able to solve nonlinear systems of equations. So instead, we will learn how to solve them using Python. It's still going to be useful to solve systems of nonlinear equations. Ask your colleagues that are just a year or 2 years ahead of you. They'll tell you, oh, we are solving time-dependent ODEs that are nonlinear. So they have not only doing ODE int, they're doing fsolves within ODE ints for systems of equations, okay? So we're going to build the foundation here by doing the fsolve for systems of equations. Okay. So here's how we're going to standardize this for a general system. For an arbitrary system, you're going to first define and write down the residual function for each and every function. Okay, each and every equation. You have 7 equations. You're going to have 7 residual functions. You are going to need to list your variables of interest. Here I'm calling them x1, x2, xn. They could be x, y, t, w, or they could be t1, t2, t3, t4, t5, right? Or they could be h, r, v, and l, right? Just write them down so that you know what you're dealing with. And then each one of those residuals is in general a function of all the others because they're all codependent on each other, right? They're all dependent on each other. The system that we just looked at, we had x and y as our variables of interest, and each one of the residual functions was a function of x and y. Okay? Then what that means, all of your residual functions make a vector of residual functions. Okay? This is just the conceptualization. So you have a vector of residual functions. I'm laying down the foundation because this is all you're going to need for Python. Okay? This is all you're going to need for fsolve. Okay, so let's see how we do it. You first define a Python routine to compute the residual vector, this R. So your objective is to define a Python routine that computes a vector of R1, R2, R3, R4, R5, all the way to Rn. 5 equations, 5 Rs. So that routine needs to return an array of values that contain the residual functions at whatever guess you're working with. Remember, numerically, all of these functions are working with numbers. Okay, so you pass information to the routine, it's going to return an array of numbers, that's all. The input to that routine, when we had a single unknown, single variable of interest, we had only one input, x. Initially, it passed the x0, and then it passed x1, computed the residual, returned it, etc. In this case, your input needs to be assumed to be an array of values. Okay? How do you do that in Python? I'll show you in a minute, but you just call it x values, but you know internally that I'm passing an array to that subroutine. Now be careful. The order of those variables is going to matter. You have to decide, am I going to put R, H, V, and L, or am I going to call them L, H, V, R? You have to be careful to choose that order, because once you go inside the routine, you're going to take the first variable and plug it in the right spot to compute R1, the second variable, same to compute R1 and R2, and so on. Okay? So for example, if we were doing this system that we just looked at, the example, we had these two residual functions, half x cubed plus y minus 4x, and y minus sine x e to the minus x. Okay? This does look like a vector. This is my residual. Let's take a moment to look at it. Define, standard definition of a Python routine. I'm calling it residual. Okay? I'm assuming an input, I called it vars, to insist that, to remind me that this is a collection of variables. Now, I'm assuming that in this vars, the first value in vars corresponds to x, and the second value corresponds to y. So I immediately pull those out from this vars array. Why is it an array? I choose to be an array. You can pass a single value, it won't be an array, but if you're doing things consistently, you're going to be passing an array. And the order I chose is x and y. So I know in my calculations that var 0, the first entry in vars, is x, and the second entry is y. Then I compute R1 and R2 numerically. So now I have concrete values here, numerical values. Then I simply compute R1, which is 0.5 x cubed plus y minus 4x. And R2 is y minus sine x e to the minus x. Now I have to return the residual vector to fsolve. Okay? So I return a NumPy array ordered as R1 and R2. That's it. That's a residual function. Now you plug this into fsolve. How? Just like we were doing before. You call fsolve and give it a residual. For fsolve, it doesn't care if the residual returns a single value or an array of values. It doesn't matter. It's just going to solve it. If it gets an array of values, then it knows it's a multidimensional system of equations, right? But what's going to matter is the initial guess. You don't have a single initial guess now, single value. You have an array of initial guesses, okay, for each of the unknowns that you're solving for. All right, let's do this together in Python. Get your notebook. Okay, let me close this guy. So we can work with the same notebook because we already have the fsolve imported. Okay, so let's just call this a systems of equations with fsolve. Okay? All right, let me get my slides. I just need to remember the equations. Don't copy the code yet. Let's just write it together. Okay? I'm going to define my def residual, or my residuals. Let's change things. Okay? Be very creative. My residuals, okay? And vars. So I'm solving these two residual functions, okay? R1 is 1/2 x cubed plus y minus 4x. And R2 is y minus sine x e to the minus x. I choose to treat my vars. The first value in vars is going to correspond to x, and the second value is going to correspond to y. Okay? You make that choice. X is equal vars 0, and y is equal vars 1. Okay? And then R1 is simply 0.5 times x cubed plus y minus 4x, right? Plus y minus 4x. And R2 is y minus sine x e to the minus x. R2 is equal y minus mp dot sine x times mp dot exp, what is it? Minus x, right? And then simply return a numpy array. So we need to return the list of residual functions. And we're going to do R1 and R2. Now, why that order matters here? Because the return value that fsolve is going to return is going to return the order you chose here. So the first root that fsolve returns is going to be the root for x. And the second root, the second value is going to be the root for y. If you swap the order, then fsolve is going to swap the order. Okay? All right, so let's go back to this function and this plot. And let's say, I don't know, we want to get this root. Okay? Let's say we want to get this root. So let's choose a value for x equal 3 and a value for y equal 0. Okay? So fsolve. First, are we all in sync? Okay. So fsolve, my residuals, that's it. Then we're going to give it an initial guess. The initial guess is going to be, what was it? 3 and 0, correct? Are those? Yep, those are the values I chose. Let's see. Oh, look at that. It's at 2.83 and 0.02. That looks right. Okay? Let's try to find the other root. So let's say, well, this one's 0, 0. What about this one? We got a minus 1.5 for x, and let's say minus 6 for y. So minus 1.5 and minus 6. Okay, so minus 1.5 minus 6. Okay. Look at that. Okay. It's, what is it? Minus, what was it? Minus 4.3. So it's right here. Okay? Minus 4.3 for y, and for x, minus 1.4. Seems like, huh? That was easy, right? Okay, wait until we program the system of 1,000 equations. Okay. Once you figure out how you can create an array of residuals, okay, it's just easy then to solve those for those roots. Okay? Any help needed? Okay. Keynote. This is what my slides look like. So at the end, you'll see the additional material. You see a lot of things. So if you want to take a look at what Newton's method looks like for multiple dimensions, you're going to have to do the Taylor series in multiple dimensions. You're going to have to do Jacobians, and it gets pretty complicated after that. So yeah. Anyway, we decided not to do that this year, but you're welcome to look at the slides. They're self-sufficient, okay? So now let's go back here, and let's see. We did this together in class. Now we're going to go back to our system of larger system of nonlinear equations for the heat transfer problem. This is a real problem. It's not just a toy problem. It's a realistic problem, okay? So we have the discrete form of the equation at every point. So this is a template equation, right, that applies at points 0, 1, 2, 3, all the way to the end, correct? So from that equation, we can then derive, the first order of business is to define or deduce the residual function at any point I, right? So that's what we're going to do. We're going to define Ri as the residual at point I, and I'm going to move everything to the left-hand side. So it's ti plus 1 minus 2ti plus ti minus 1 minus alpha delta x squared, ti to the 4 minus t infinity to the 4. I don't have to combine ti to the 4 and ti. They're not usually combinable. So I can just put them just like that. Okay? That's my residual function at any point I. Okay, question. What is the residual function at the left point, at t0? So remember, t0 was equal to t left. Agreed? So what is the residual r0? Remember, we don't apply this equation at the left point and the right point because we know the values there. They're given to us. Those are the boundary conditions. So t0 is equal to t left. t0 is an unknown, right? And it's equal to t left. So what's the residual? Minus t left, yes. What about the right point? Tn minus 1 or Tn, right? Exactly. So that's a critical. You're like, well, t0 is equal to t left. That's just an exact value. Yeah, that's fine. You can define a residual from that. When the residual is equal to 0, it means t0 equal t left, which gives you this answer. So it's a kind of a trivial residual value. But we need it because that's the residual at the endpoints. Same thing at the last point. The last point in our indexing is Tn minus 1 equal T right. So that means the last residual is simply Tn minus 1 minus T right. So that residual idea doesn't only apply to nonlinear equations. Linear equations are a special case of nonlinear equations. You can do fsolve to solve systems of linear equations. It's going to do a Gaussian elimination on that, okay? All right, so let's go ahead and do this together. Actually solve this system of thousands of nonlinear equations. And we'll do it in a loop way where it doesn't matter how many points we put in. There's no more diagonals here, no more upper diagonal, no more matrices, because you cannot build a matrix out of this. You can't. Okay? Matrices are only for linear systems. You can't build a matrix out of this. Okay? So let's see if we can do it together in class. We can do it in this same notebook or start another one if you prefer. Okay, let's see. Actually, I'm going to need plotting. So let's do it in another notebook. Okay. So I'm going to do import numpy as MP. And we're going to do from scipy.optimize import fsolve, right? That's our key function. And matplotlib, because I want to plot the temperature. matplotlib.pyplot splt, and then I'll do the magic matplotlib inline, and then config inline backend.figure format is equal to SVG. You don't have to do the last 2 lines. Highly recommended. This is going to be a little less coding than when we did the linear system or the linear case, but the coding is a little bit more involved. Okay? So first we're going to define some dimensions for the problem. L is 1.0 in meters. Okay? And number of points or number of nonlinear equations is, say, 200. And dx is the interval size, which is L over n minus 1. Remember, the points are at the edges of the interval. So you have n points, therefore you have n minus 1 intervals. And then for plotting facility, x, the location on the rod, is np.linspace from 0 to L with n points. Okay, are we in sync? Okay. So now I want to define some properties for the problem as well. We can continue defining them here. Well, let's just do it here. T left, let's say, is equal to 400. Then K. Then T right is also 400, let's say. Okay. Okay. For I have here, let me see. So we had an alpha, which is also a kind of heat transfer coefficient. Okay. This alpha combines the ability for the heat to be transmitted along the rod, but also the ability of the air, or not the air, the radiation, to be transmitted to the rod itself. Okay. So the combination of those two, I call it alpha. That could be really good range but for a bunch of values. So let's say alpha is equal 1e to the minus 2. Okay. And then finally, T infinity, let's say, is 450. Okay. Now let's define the residuals. Define residuals. Okay. T infinity is the ambient temperature. Okay, it's the temperature that you expect for the ambient surroundings to be at. Okay, in this case, for radiation, right, it's kind of the expected temperature that the radiation is going to create in the environment surrounding the rod. Okay, because right at the rod's surface, there's going to be a temperature gradient that is driving heat one way or the other, right? And that temperature gradient, you need the difference between the rod temperature and the temperature around it. We call that T infinity. Okay? It's clearer when you have air blowing at something, right? Because you know, oh, I'm blowing cold air through my hairdryer, right? And so you can kind of define that temperature, which is maybe the room temperature, or if it has a cooling coil or something, right? You can define that temperature. Okay. Now I'm going to call all my variables as T, because I'm going to try to access the T array, Ti, Ti plus 1, etc. So I don't want to call it vars, so I don't have to type vars and then open brackets I and I plus 1. I'm just going to call it T. Now T, I expect this to be an array, okay? An array of values, T0, T1, T2, T3, and so on. Okay? So first, because this contains, could be 10 equations or 1,000 equations, I'm not going to hard code that array. I want that array to be created automatically. So instead of what we did in the example where we had only 2 residual functions, I'm going to create an array of zeros with the same size of the number of equations that I have, or the number of unknowns, right? Not matrix, and a single array, okay, to contain the residual vector. In the previous example, we kind of hard-coded return np.array r1, r2, right? This case, it doesn't make sense to do that because I might have 1,000 equations. I'm not going to hard-code those. So instead, I'm going to take the other route. I'm going to create an empty array of zeros and fill in the values as needed. Here's how I do that. I say n is my length of t, which is the length of the system, the size of the system. In other words, how many equations we have, and also how many unknowns we have. So you agree now that n, or do you? I hope you agree that n is the size or the number of equations that we are dealing with. Then I create my residual vector by saying np.zeros of size n. What this does, I initialized an array, I filled it with zeros, and I'm going to, one by one, fill in the residual values. One by one, I'm going to go ahead and fill in the residual values. What is the first residual value, R0? TL. Yes. So R0 is TL. There you go. We know the first value. We also know the last value, okay, which is R at -1 is equal T right. We did make a mistake, though, because our R0 was T0 minus TL. And our R to the end, the last R was Tn minus 1 minus T right? So we made a little mistake here, but that's good because now it shows us that we need to index T. So I'm going to do T0 minus TL, simply, and T, last T minus TR. Okay? Or you could put Tn minus 1 minus TR. Yes? Which one? Okay, so I'm putting here, I'm simply implementing the first and last, these 2 residuals. This R0 and this Rn minus 1. Okay? So first you agree that these are the residuals at the endpoints. Okay? Okay, now that we agree on that, when I created the array of residuals, because I don't want to go and put each one of them and return it. Instead, I created an array of zeros. I'm just going to fill it in as I go, as I loop through the equations, through the points. But I know the first 2 points very easily in that residual function, which is R0. The first entry is simply T0 minus T left. Now, what is T0? It's the first variable in my array. Right? We have an array of values. So in the example we did where we had an x and y, vars 0 was x and vars 1 was y. In this case, T of 0 is T0, right? And T minus 1 is Tn minus 1. It's the last point in the solution, right? We're solving for T0 all the way to the end, to Tn minus 1, right? So I need to access that T0 simply by T of 0. Is that clear, Brandon? Okay. Remember, this T contains the array, is an array of your solutions. T0, T1, T2, you can access them. You should assume here in the routine that this is given to you. Okay? This is going to come in through fsolve. Let fsolve figure out how to pass it. But you're getting that array. You can access each and every point. Okay? So now I need to fill in the residual for the remaining points. So in other words, I need to fill in all of these Ri's. Okay? So I'm going to start looping from 1 to this last point. Okay? So this indexing here is messed up, unfortunately. So let me show you the indexing over here. So we're going to start with T1 all the way to Tn minus 2. Okay? We're going to start from T1 to Tn minus 2. and fill in the residual values. Okay? This is the formula for the residual. And I'm going to do this with a for loop. I'm going to go for I in range from 1. I'm going to start with T1, right? R1, because we have R0 and we have the last R. So I'm going to go from R1 to the one before last. Okay? So my range is going to be from 1 to n minus 1 because this is an open interval. So it's going to go R1, R2, R3 all the way to Rn minus 2. So watch this now. Ti minus 1 is Ti minus 1. Ti is simply Ti. And Ti plus 1 is equal Ti plus 1. And guess what? Ri is equal to, what is that formula? Ti plus 1 minus 2 Ti. Let's see if we can put it on the side. There you go. I'm simply writing the equation. Even I'm using the same indexing. Ri is TIP1, or I plus 1, okay, minus 2 times Ti plus Ti minus 1 minus alpha, okay, times dx squared times Ti to the power 4 minus T infinity to the power 4. Oops. Left.
Why is the range from 1 to n minus 1 instead of n minus 2?
Because it's an open interval at the end. The range function, doesn't hit the last point. It hits the one before last. Okay?
So Ti minus 1 is basically Ti minus 2.
No. This is correct. This is saying at I equal 1, this would be T0 and this would be T2, right? So this would be R1 is T2 minus 2 T1 plus T0, right? So it's exactly as it is. Just the end points, the first and last points, we had different information for them. Yes?
On the bar in the diagram, why is the last point
The indexing is incorrect on that one. Sorry. So the indexing, the right indexing, I didn't update it on that figure. I updated it here. Right? So we're going from 1, we're covering the internal points, okay? Only the interior points. Not the last one, the first one and last one, we covered them here, right? Those are the first and last point, okay? Now what do? We filled out the entire set of residual functions. We filled out the residual vector, right? R0, R1, R2, all the way to the end. It's just numbers. All I have to do is return it, just like we returned it in that other example. Return R. Okay? Let me maybe zoom out a little bit. Okay. So in many ways, this is actually much easier than when we were dealing with the linear system of equations, because we had to do main diagonal, upper diagonal, lower diagonal, and this and that. This is just hitting the residual functions. So now all we have to do is solve it. fsolve, residuals, and I need an initial condition. Initial condition. Okay. What would you suggest we provide for an initial condition? This is a case where we can't visualize the system, right? Like we did before. We said, oh, maybe there's a root between minus 4, etc. Ethan.
Well, if it's like an initial condition, then maybe like the temperature of T right or T left.
Okay. It's an initial guess. It's not an initial condition. It's different. But you're entirely correct. I mean, it's a heat transfer problem. You know, we're doing radiation on the problem. T infinity is like 450, and T left and T right is 400. The temperature is going to be somewhere in between. So I could initialize it with 400 or 450, right? Or 350, right? Or 425. Yeah? 425? Okay, you like the 4. So we're gonna do the miles temperature, miles initial gas is equal 420.
God, you spelled my name right. Oh, right.
No, but I didn't read it actually. I didn't read it right now. Hey, come on, Lev, don't ruin the moment. Okay, if I provide 425, that's a single value. So I need it to be an array. Okay? So I just multiply it by np dot ones of size n. Okay? We still haven't defined n, right? Or actually, we did define n. Sorry, it's right over here. Okay, we did define n. Okay. And then we're going to call this the miles initial condition. Let's store it in a variable called t solution. It did something. Okay. Did it do something for you? Error?
No error codes.
No error codes. Okay. Miles is going to help you. Did you guys get a solution? Did you get something? Okay, so let's plot it or print it. I'm going to plot it. So I'm going to do plt.plot of t solution versus x. Oh, look at that. Oh, wow, it's pretty flat. Right? Look at that. It's just the radiation heat transfer completely dominated this.
What are we solving for again?
For the temperature, okay, in the rod.
At every point?
At every point, okay? So now I'm going to reduce this alpha. Okay, look at that. So I've reduced now alpha. Alpha is a measure of how fast heat transfer is being transmitted to the rod and along the rod, okay? The smaller the alpha, the less that heat is going to be communicated as fast as we would like. So now I dropped alpha to 10 to the minus 7, and this is what I got. We're solving for the temperature in the rod. This is a rod subjected to heat transfer, okay, through radiation. Are you getting these plots?
So fsolve can solve
10 to the minus 7. Just play with it. Play with the values.
fsolve can solve an array of residuals.
Exactly.
Whoa,
A system of nonlinear equations.
that is so cool.
This is a system of nonlinear equations. We can change the value of n for all we care. 300. No, you're doing 300 nonlinear equations, or technically 298 because the first and last ones are linear, right? We solve it. It's going to be same good old thing. A good reassuring thing is that our endpoints are exactly what we intend them to be. If you're getting different values at the endpoints, means there's something wrong with your system. Connor.
So in this example, would this be like the ends? How are the ends fixed at 400? It's just like they're being cooled, or
Being cooled or in a bath in a sink or source of water, right?
yeah.
Okay. That becomes a problem for the experimentalist. You have a question? Did you have a question? Okay. You got it? Yeah. Okay. Change the temperatures. See what happens. Let's say, you put 300 on the right. Oh, look at that. 300 on the right, 400 on the left. Okay?
What did you set n to?
300, the number of points, n or alpha.
Oh wait, no. Oh, you changed alpha.
Alpha. I changed alpha to 10 to the minus 7. Put it 10 to the minus 5 if you want. With large values of alpha, larger values of alpha, we saw this flat curve, right? Because the heat was instantly transmitted to the rod and dominated it, right? But with smaller values of alpha, there's more resistance for that heat to be absorbed and communicated along the rod. Okay?
Rounding error. When I change,
No, this is, you change it to,
I change it to a very small number.
yeah, so then the system might not be valid in that case. So that's it's a very extreme situation. I don't think you can, yeah, because then in that case, the heat transfer coefficients will become dependent on the temperature. There's another nonlinearity that comes in. So it's not a good representation. Yes, Ethan.
If we only had one temperature reading, like say we only knew the temperature of like where some thermocouple was in our system, and it was in the middle of it, would we still be able to solve the system?
Yeah, well, that's a problem for ODEs. We're not, it will be ill-posed. You need to know enough boundary conditions that is consistent with the order of the equation. So this is second order differential equation, so we need at least two information. Yep, two pieces of information so that we can close the system, right? It's those endpoints, right? Because if you keep applying that residual function, like there's one point that you need to know. There's 2 points, one on the left, one on the right, for example, that you need to know, right? So, yeah. Those become more on the modeling side, right? With the numerical method side, you kind of have it well defined, right? That's what we're doing here. Yeah, yeah. Nonlinear systems of equations. You are gonna see this. You are gonna remember this lecture, okay? It's gonna be on YouTube. It's gonna be in your slides, in your hard drive, okay? Because you're gonna see this, okay? Today, some of your colleagues heard me discuss it with one of your other colleagues in separations, I think, or mass transfer. They had to deal with this system of nonlinear equations. And so you'll see it. All right?